This is section 3.1 on the derivative of a function. This is a key concept in calculus, and is in fact one of the reasons why calculus was invented, so that we could actually find the slope of a curve at a particular point. So we can define the derivative. We talked a lot about where it came from in the last section. The derivative of a function f with respect to x, okay, is defined to be f prime of x, which we know, which we talked a little bit before, and with rates of change, it's the limit as h goes to 0 of f of x plus h minus f of x all over h. Now we can also define the derivative, okay, to be the rate of change of f at x. It's also the slope of a curve or a line at x, okay, and it's also defined to be the instantaneous rate of change at x. So let's look at some examples, kind of using this standard limit definition with limit as h goes to 0, and then we're going to look at an alternate definition. The first one is, let's say that I want to find out if I let f of x equals 5x squared, and I want to know what is f prime. So let f of x equal 5x squared, and I want us to find f prime of x. So I'm going to set it up, limit as h goes to 0 of 5x plus h squared. Again, everywhere I see an x, I'm plugging in an x plus h based on my formula from above, minus 5x squared all over h. Now again, it's a limit, so the first thing I'm going to do is try to plug in 0, because it's limit as you go to 0. So when I plug in 0 here, I'm getting a denominator that's undefined, so I know I have to do some algebra on that. So I'm going to look at the limit as you go to 0 of 5. I'm going to distribute out that binomial, minus 5x squared all over h. Again, I'm going to try to plug in h to be 0 again. I'm still getting something that's undefined, so I need to do some further work. So 5x squared plus 10xh plus 5h squared minus 5x squared all over h. And now nicely, these 5x squareds can cancel, okay? And my next step is I'm still trying to plug in an h. My next step is I'm going to take out an h. I like to be able to do that because then the h's can cancel at the bottom. So the h's are going to cancel. And now, okay, I can actually plug in that 0 there for h. And I'm just going to end up with 10x. So I'm going to say that f prime of x is 10x. Now what that does is approximate the slope of the curve anywhere along that parabola of 5x squared is going to be 10x. So if I wanted to know what the slope of the curve was, if I wanted to know what the slope of the curve was at x equals 2, I could just say that f prime of 2 was equal to 10 times 2, which is 20. Let's look at another example here that involves a little bit more algebra. So let's say that g of x was the square root of x plus 2, and I want us to find g prime of x. So again, I'm going to set up my limit definition. Limit as h goes to 0. Everywhere I see an x, I'm going to plug in an x plus h. So that's my x plus h, which is replacing my x up here, plus 2 minus the square root of x plus 2 all over h. Again, in each step, I'm going to try to plug in h equals 0 because it really is a limit. Here, that's not going to work. So I'm going to take the limit as h goes to 0. Now, interestingly enough here, this kind of looks like a place where I could potentially multiply by the conjugates. It's a nice algebra example that we've used quite a bit. So I'm going to multiply by the conjugate here, square root of h plus 2 plus the square root of x plus 2. And again, 1 is a very powerful number. I'm really just multiplying by 1. I'm not changing the problem because I'm multiplying by 1. Again, I can't plug in h to be 0. And now I'm going to do some work on the top. Since it's a conjugate, I really only have to worry about the two outside terms because the inside terms are going to cancel. So minus x plus 2. And I'm not going to do much simplification with that bottom. X plus h plus 2 plus the square root of x plus 2. I'm just going to kind of leave that for now because I think we're going to see pretty nicely what happens there. So again, I can't plug in h to be 0. So I'm going to look at that limit. So I'm going to get on the top, I'm going to get x plus h plus 2 minus x minus 2. I like that because a lot of things can cancel. And again, I'm just going to kind of leave that piece on the bottom, x plus h plus 2 plus the square root of x plus 2. And then on the top, still got that h in the problem, which is going to leave my denominator to be undefined. On the top, I think we can see that the x's cancel, the 2's cancel. Now I just have h over h times the square root of x plus h plus 2 plus the square root of x plus 2. And now the h's can cancel, leaving me a 1 on the top. Be careful about that. It doesn't cancel out to be 0. And then at this step, I'm going to kind of plug in h to be 0, because I think we can see what happens there. So it's going to be the limit as you go to 0 of 1 over, oh, this is pretty nice, x plus 2 plus the square root of x plus 2, which is just equal to 1 over 2 square roots of x plus 2, because I'm adding those together. So that implies that g prime of x is equal to 1 over 2 square root of x plus 2. And again, you can plug in any value of x there. Let's take a minute and look at the alternate definition of the derivative. This is kind of one that you might see come up. And then we'll look at some examples. So we have the alternate definition of the derivative. And I'm going to kind of write it out first, and then I'll show you where it comes from. So it's the limit. Again, that limiting factor idea is coming in as x goes to a of f of x minus f of a all over x minus a. So if I again draw a similar picture here, I'm going to kind of do a visual the best that I can. Okay, I'm just going to draw a curve that's pretty sort of flat, curvy there, so that I can show you what's going on, if you will. And now I'm going to draw that secant line idea, the same thing that we saw before. Okay, I'm going to call this point over here A, and I'm going to call this point here X. So this right here is going to be x f of x, and this point over here is going to be a f of a. Now on this point it's negative, but that's okay, we can still call it a. So again, you can see where this idea comes from. Essentially what we're doing is we're again looking at that idea of the secant line. So we're just finding the slope of the secant line. Again, remember that derivative represents slope. This is just simply the slope. Now when I add that limiting factor in there as what happens when x goes to a, look at what happens here as you let x go to a here, if I can kind of arrow over. what we're essentially doing is we're reducing that distance from x down to a. So when we reduce that distance, okay, we're essentially going to get that tangent line which touches at one point. So we're going to get that tangent line that just touches at A there. Okay? So let's look at some examples about how this could work. I'm going to use the same one that I did before. Okay? So I'm going to let f of x equal 5x squared. And again, I want to find f prime of x. But this time I'm going to use the alternate definition of the derivative. So I'm going to let the limit as x goes to a, okay, be f of x minus f of a. I'm just going to write it out so we can recall what it is. Now I'm going to see what I've got. I've got the limit as x goes to a. Again, it's a limit, so I'm going to try to plug in a. When I try to plug in a up here for x, I get a minus a on the bottom, which makes the denominator undefined. So now f of x from up top is just 5x squared. F of a is just simply plugging in a for x, so it's 5a squared, all over x minus a. Again, I try to plug in a, and I'm getting a denominator that's undefined. So let's do some algebra. Limit as x goes to a, I'm going to take out a 5. I get x squared minus a squared, all over x minus a. Okay, and now it looks like I can factor the top to be x plus a. I know that is the difference of perfect squares. I like that. All over x minus a. Now, conveniently, my x minus a's cancel here. Those factors cancel. And I'm just left with 5 times x plus a. And now what I have to do, I'm going to sort of rewrite it down here. Limit as x goes to a, which is 5 times x plus a. I'm going to now, the limit tells us to plug in a for x. So I'm going to plug in a for x. And I just get 5 times 2a, which is 10a. So therefore I know, okay, that f prime of x, okay, or in this case, we're going to have, we let it go to a. So therefore I can see here, all right, that f prime of a is just going to be 10a. So I can plug in whatever I would like there, okay, into the a value. So if I want to know if a is 2, and I want to know what the derivative is at 2, I can plug in there to be 10 times 2, which is 20. Okay? So that's sort of the alternate definition of the derivative. And you could do a similar type of example for the square root function as well.